On a standard downhill ramp, the rules of physics are straightforward. A shorter distance guarantees a faster finish. If we release two objects on straight tracks of different lengths at the same time, the result is predictable. The racer with less ground to cover wins every time. However, those rules change if we replace the straight ramp with a smooth, wide bowl. Four identical racers sit at different heights on this slope. The top racer must travel nearly 10 times further. When released, something unexpected happens. Despite different starting positions, every object reaches the center at the exact same millisecond. This curve is known as a tautochrone. The name comes from the Greek words for same and time. This result contradicts our intuition that distance dictates the clock. On this specific track, the head start doesn't matter. To see how this works, we can look at the racer placed closest to the finish line. This bottom section of the curve is almost completely flat. With very little slope, gravity has little angle to pull on, causing the object to roll slowly. The very top of the track is the exact opposite. Here, the curve is effectively a vertical drop. Gravity seizes an object at this height immediately. It falls straight down, gaining a massive burst of speed through the flatter sections. Acceleration changes depending on where you start. The higher the starting point, the steeper the drop, and the faster the speed. Gravity acts as a built-in equalizer. It provides the furthest racers with exactly enough momentum to compensate for the extra ground they have to cover. While a steep drop provides more speed, it's still surprising that the timing results in a mathematically perfect tie. This precision is possible because of a geometric shape called a cycloid. A cycloid is generated by tracking a single point on the rim of a rolling wheel. As the wheel moves forward, the point traces a series of distinct arches. Flipped upside down, one of these arches perfectly matches the shape of our racetrack. Because of how a wheel rotates, this curve possesses the exact rate of curvature required to cancel out extra distance with increased speed. As long as the track follows this geometry, the tie is a mathematical certainty. The Tautochrone is the physical manifestation of this geometric equation. In the 1600s, this curve solved a major crisis in maritime navigation. Shipboard clocks were notoriously unreliable because the rolling of the sea interfered with the regular swing of the pendulum. A standard pendulum swings in a circle, and as it loses energy, its swings get shorter. Because a circular path isn't a tautochrone, those shorter swings take a different amount of time, causing the clock to lose its accuracy. In 1659, Christian Huygens realized that the solution lay in the cycloid. Huygens added curved metal cheeks to the top of the clock's pendulum. These were shaped like cycloids so that as the pendulum swung, the string would wrap against them, physically forcing the weight to follow a tautochrone path. This ensured that every swing took the exact same amount of time, regardless of its width, giving sailors a reliable way to keep time on the open ocean. In most races, starting far behind the pack is an insurmountable disadvantage, but on this specific curve, the physical forces are so balanced that every head start is perfectly neutralized. The cycloid creates a rare environment where, regardless of where the racers begin, they all cross the finish line together.